Hi, these are edited versions of the lectures that I taught synchronously over Zoom. I hope you find them useful. I guess we're good, ready to start. So do you guys have any questions about before? Otherwise, we're going to get ready with lecture 14. This is the second part of the lecture on inference in moment inequality models. If you remember last class, we discussed examples that will lead to moment inequalities. We talk about entry games, missing data. We talk about the properties that we wanted from a confidence region, and we discussed two methods to do so, which were the least favorable test and subsampling. Today, we're going to keep moving into the so-called moment selection. But before I do so, I'm going to go back to the main intuition behind these two, where, as I said, I plan to sort of like answer some of the questions that you had before. And hopefully, we're going to have everything we need to move to moment selection. One topic that I'm going to skip today is this on subvector inference. All right, the slides are here, so you're going to have the slides. Of course, these are taken from the paper that I wrote with Azim. But to do this well actually requires 3 lectures. So I'm debating moving forward I'm pretty sure moving forward, I want to do this in 3 lectures as opposed to 2 so that I can explain it better. In particular, if I want to focus more on some advice or guide to practice, okay? But this year already allocated 2, and so we have to work with 2, okay? So notation, it's just the same slide that I wrote last time. I just gonna use this, and I want you to have it fresh in my mind. Remember, p hat is the empirical distribution of the data. We're gonna use that, particular when we talk about the bootstrap. Whenever you see p hat, is because we're gonna be using the bootstrap. Then mu theta p is the expected value respect to p of the moment function, which is a function of the data w, and the parameter of interest theta. Remember that we're going to be using models that are going to be moment inequalities that are going to say that this is less than or equal to 0. So we're going to use that. The sample analog of those moments m is going to be m bar. And omega hat is the sample correlation matrix, which is a matrix that will have 1 in the diagonals and correlations outside the diagonal. The population variance of each moment is going to be sigma squared j, which is a function of theta and the distribution p. And the sample variance is going to be the same, but it's going to be indexed by n, okay? So it's going to be sigma hat square nj. And finally, the matrix that we said we're going to use to standardize moments is this matrix D, which is going to be the diagonal of all the sample standard deviations, okay, sigma hats. And we're going to see D hat inverse floating around, which is a way of getting m bar divided by sigma hat kind of like everywhere, right? So remember that we're going to see d hat and inverse theta, times m bar theta. This expression is going to appear frequently, and essentially this is going to be mn bar j theta divided by sigma hat and j theta for j going from 1 to k, whatever. Okay, so that's what we're going to be doing. So let me revisit this idea that we talked about last time, and then some of the questions came from this trick, okay? And this is normal, by the way, because again, as I said, this trick of using this auxiliary distribution is something that we did with Azim in the paper, trying to, as I said, provide a unified framework to explain all these methods. But it was a way that we thought about the problem, and it's kind of like I don't want to say advanced, but it's something that comes after thinking about the problem for a long time. So it's not so easy to grasp initially. But let me try again. The test is going to involve a test statistic Tn theta, and as I said, we're going to consider different ones. They are all a function of 2 components. The first component is d hat inverse square root m bar, which is what we just said, is scaling the moments by the standard deviations. And the second part possibly is the correlation matrix, okay? there are a lot of these, a lot of these estimators that actually don't depend on the correlation matrix, okay? Others do. For now, just to simplify what I'm going to see next, I'm going to just ignore this. Doesn't matter. Just for notation, this saves me space. And then we came with this auxiliary distribution, which essentially depended on a random variable that was normal, this Zn theta, or asymptotically normal, and a function that we call S of theta. Okay, the other elements are known. And this auxiliary distribution was the distribution of the test statistic evaluated at this expression, right? Which is this long thing. And the question is, why is this useful? Let me go over this again. So what we want is the distribution of the test statistic, which is the probability that the test statistic is less than or equal than whatever number x. So if I use what I have on top for this test statistic, this is t of d hat inverse n theta times square root n bar and theta less than or equal to x. Again, notice how I'm not using the omega hat for simplicity so that we have shorter expressions. That's the only reason, okay? So what I'm going to do now, here I'm going to say add and subtract d hat inverse theta the square root mu, the true mean. Okay, I'm going to add and subtract that object. So what I have is the probability that the test statistic of d hat n inverse theta times square root n. I'm going to open parentheses again, n bar minus mu theta p plus d hat inverse n theta times square root n mu theta p. So I just added and subtracted the true mean scaled by square root n divided by the sample standard deviation, this d hat inverse business. And so here I said the following. Well, first, notice that this square root n times n bar minus mu is the object that we're calling Zn theta. It's an object that is asymptotically normal. By some CLT, just square root n bar. Here we have ID data, so it's the usual CLT, and it's going to be normal with mean 0 because we're centering at the true mean and some variance, which we don't know is going to be sigma in the notation that we use at some point, okay? But it doesn't matter. And then we have, in the other part, we have this term here that we said is hard, okay? Hard because if we estimate this by square root n bar, which is the usual estimator for square root mu, then the difference between the square root n bar and square root mu is big OP1. It doesn't converge to 0. It's actually normal, we say, right? Big OP. So let me stop here for a second before I keep going and notice that somebody asked, why does the distribution depend on a square root n mu? Well, here you see why. It's just you add and subtract. It's just things are being multiplied. The drifting factor, the factor that you don't want there, which is this part, right? That you would prefer not to be here, depends on the square root n times mu, just by how things are. It's the usual argument when you're not properly center, if you want. All right, let's keep going. So this distribution, okay, is greater than or equal than the probability, and I'm going to copy everything. Let me just do some space here. Is greater than or equal than the probability that the same thing, I'm going to copy pretty much the same. Actually, sorry. Let me just use Cn theta. So the probability on top is greater than or equal than the probability at the bottom, provided the square root mu theta p is less than or equal than S of theta. Okay, and why is this the case? Because the test statistic is monotone. Okay, and so if we keep everything the same but replace with something, oh, sorry, this, I screwed up here. Oh, I wish I could move this. Can I move this? Yeah. It's fancy. Okay. There you go. And then, oh, I see that we have multiple mistakes. You guys are not paying attention. You should tell me, like, hey, you're missing things. There we go. So the probability that this guy is less than or equal to X is greater than the probability that this guy is greater than or equal to X, because this S is higher than square root mu. Okay. And the test statistic is monotonic. So now somebody asked in the report, said like, well, I didn't see why, say in subsampling later or things that we're gonna talk today, how this S function business is consistent for square root mu. And the answer is, well, it is not. The approaches that we're gonna describe are not about getting square root mu consistently. We cannot estimate square root and mu consistently. But the goal is to find, a valid upper bound, some function that is above. And why is that the case? Because then we have this inequality over here. And this inequality means that is going to mean that the quantile with S is going to be greater than or equal than the quantile with square root mu. Okay, and that's the deal. We're going to be able to compute this quantile, which is not the quantile that we want, but it's going to be at least as big as the quantile that we need. And whenever we use quantiles, critical values, that are at least as large as the ones that we want, we're going to have valid inference. If they're too large, it's going to be conservative, but the inference is going to be valid. So the goal is not to estimate a square root and mu consistently. We can't do that. The goal is to find valid functions S that satisfy this inequality that we wrote here. So does this address some of the questions that you guys asked me in writing? So now let's keep going. What's the idea behind least favorable and subsampling? Well, again, the probability distribution of the true test statistic, the one we would love, is the auxiliary distribution at square root n mu. We just saw that, okay? This is hard, so we're going to use this one with a function S. I highlight here, we're using S. And so in the least favorable case, we know that square root mu is less than or equal to 0, because that's what the model says, right? It's a moment inequality model. Whether we scale by square root mu doesn't change anything. And so the quantile of the distribution with the true mean, which is the one that we want, is bounded by the one that includes 0. Okay? This is exactly what I wrote here. The quantile using the function S is going to be at least equal to the quantile that uses the true thing. So here it's flipped, but it's the same thing. And in subsampling, well, remember that these moments are negative, right? Whoops, I didn't want to do that. These moments are negative. So you have 0 here. And let's say that this is mu, because it's negative. Well, if you multiply mu by square root b, and this is, greater than 1, this is going to be here. And then by square root n, it's going to be here because n is larger. So you have that the square root n mu is less than or equal than the square root mu because n is, because b or n is much greater than b. So the quantile that you want, which is this one, is bounded by the quantile that you can compute, which is this one, which is the one that subsampling gives you. So subsampling does not give you a consistent estimator of square root at mu. It just has the right inequality, okay? And that's why these two methods work, because, a square root and mu in both cases is less than or equal than the function s, which in one case is 0, in the other case is square root b mu. And this is why these two methods are valid. We're going to talk about uniformity later, but they're actually uniformly valid because these bounds hold uniformly over all p. Okay, and so then this works. So are there questions about this? So we're going to move to the so-called generalized moment selection. What's the main idea? The main idea is that perhaps you can say something about square root n mu. I wrote here well enough. And we're going to do this by trying to determine whether square root mu is close to 0 or far from 0. We're going to use a selection function for that. I'm going to call that selection function GMS. GMS stands for generalized moment selection. Okay, so GMS, and this GMS function can take many forms, but the easiest one is this one that I'm describing over here, where the function is 0 if your moment is, sufficiently close to 0 and is negative infinity otherwise. So if you just think about it, what you're doing is you have your line over here and 0 fits here. You have negative kappa n here. And what you're going to do is say, okay, if a square root n, n bar divided by sigma hat falls in here, I'm going to say that my moment is binding. Binding, meaning is equal to 0. So if the moment is binding, I'm going to use, 0 as a valid upper bound. Because we know that if we're binding, then 0 is where we are. Now, if the moment falls over here, I'm going to assume that, it's unlikely that we are binding. And I'm going to behave as if the moment is just lack. Okay, and remember, just in case, where is the negative infinity coming from? Well, square root n mu, okay, goes to negative infinity if mu is strictly less than 0, right? So you're trying to decide whether mu is 0 or not. At the end of the day, that's what you care about. And then you're saying, look at how this looks so similar. And this is why I teach some of the things early on to Hodge's estimator. Okay? Hodges said, if we're close to 0, we're just going to use 0. If we're from 0, we're going to use, n bar. And then there are versions of this that instead of having negative infinity here, they have a square root n bar, which is also possible. Okay, so there are different versions. This is the simplest one to me. What we're going to ask for kappa is that kappa is positive and goes to infinity, but we want kappa divided by square root n to go to 0. So remember, Hodges, we said we did it with n to the 1/4, okay, or negative 1/4 was in that case. Here in Hodges, it would be kappa divided by square root n. Okay, so then this is the idea of how this works. And then remember something else now that I told you and made the connection, right? When you do something like this, and then we saw how Hodges led to problems, right? So we say Hodges works well, but it gives us problem local to 0 and so on. In this case, this is not going to happen because in Hodges problem, when we discussed it, we were trying to get the distribution of the estimator, and here we just need an upper bound. So we don't need to show that this is giving us square root n mu, which we know that it's not going to give us that. What we want is, again, in some sense, to guarantee that a square root n mu is less than or equal than s hat GMS. We want this to be a valid upper bound. And we're going to go over that. But anyway, now take this function. And so if we just set our critical value as an estimate of this auxiliary distribution where the S function is this GMS function, this leads to a valid test. And by valid test, I mean a uniformly valid test. And this idea was proposed by Anderson Soares, and it was also used in Federico Bugni's job market paper and in my job market paper. And all three papers came essentially at the same time. The paper by Anderson Soares was a lot more complete because they just considered a lot of family, had a lot more results. Initially, as I said before, my paper and Federico's papers had point-wise results, but the main idea was the same. Okay, and so then what's the definition of a GMS test? It's a test that rejects whenever the test statistic is greater than this critical value, where you just simulate this with the GMS criterion function. So why does it work? Well, look at the following. This function depends on square root n bar sigma hat, and there's a negative kappa here that you can take to the other side. So let me just come here and do like 1 over kappa n, and then 1 over kappa n, and do 1 over kappa n here. Notice that the first term right here is big OP1 by usual CLT type of arguments, right? So square root n bar minus the mean divided by sigma. So that's an asymptotically normal term. And then this other part over here, it depends, right? It could be 0 if mu j is 0, or essentially this is either equal to 0 or it goes to negative infinity. Those are the two possibilities for that term. Okay? And so the idea then here is that if, the moment is binding, then this term here is not going to be here. And then when you have a weak OP1 divided by 1 over kappa, this is going to go to 0. So if the moment is binding, this term over here, this term, is going to go to 0. And so you're saying if this term is greater than -1, it's going to go to 0. Eventually, you're going to fall over here, and using a 0 upper bound is going to be valid because that happens when mu j is 0. Now, if mu j is not 0 and is going to infinity, okay, then this term over here is not going to be determined by this, okay, but this guy over here is going to drift to negative infinity. Or perhaps, not going to drift. It depends on the relationships of kappa and square root n. We're going to see in a minute, but definitely it's just going to be on possibly on this side. And if it is on this side and you choose 0, 0 is going to be a valid upper bound anyway. So any number that is, either 0 or negative infinity is going to be an upper bound whenever mu j is negative, because this is going to take this term going to negative infinity. So instead of trying to describe this at a level of generality, like in this case, which, I understand that sometimes it's hard to get the grasp of what's going on, what I'm going to do instead is to show you how this works in the context of a simple example. And in the same example, we're going to compare how this behaves relative to subsampling, okay? And then we're going to try to compare how both of these two learn about whether a moment is binding or not. Because at the end of the day, what these methods, all these methods are trying to determine is which moments are binding and which moments are slack, okay? So, anyway, here I just wrote the same thing that I wrote in the previous slide, okay? And based on the explanation that I gave before, I wrote here GMS provides a valid asymptotic upper bound on a square root n. So as opposed to the first two methods where we had an upper bound for every n, okay? here the bound is asymptotic. The argument doesn't hold for every n. For every n, there could be some issues, okay? But asymptotically, which is what we need, this provides a valid upper bound on a square root n mu. And as I wrote here, an alternative interpretation is that this function is selecting whether something is 0 or not. When this function is 0, it's selecting that moment as binding. When this function is negative infinity, it's saying that moment is slack. And so that's what is called generalized moment selection. It selects which moments are binding, which moments are slack. So let's go over the example. Well, no, I have some comments. So remarks, I said subsampling and comprehensive information about a square root mu, okay? Subsampling did a square root b mu. Here we have this function s that depends on the ratio. But for typical choices of kappa and b, which are the tuning parameters of GMS and subsampling, this approach is going to be more powerful. And I want to explain why in a minute. The main drawback is the choice of kappa, okay? But you can show that, there's evidence by now that in finite samples, okay? Well, let me say, there's evidence, okay, that says that the method is less sensitive to the choice of kappa than subsampling is to the choice of b. And the choice of kappa in finite sample, in any case, is difficult, perhaps as difficult as it is to choose b, because in finite sample, you want a smaller value of kappa because that always gives you more power, okay? So you want kappa to be smaller. Why is that? Again, I'm going to do it here. Remember the picture that we did? That we said 0 is here, negative kappa, and here you're saying as binding, so use 0, and here you say slack, use negative infinity. We know that 0 is at a conservative bound. So when you look at this picture, the area where you use 0, ideally you want it as small as possible because, you're better off using negative infinity when you think about power. The problem is that if you make kappa too small, then you're not going to control size because you're not going to be having a valid upper bound. Okay, so definitely there's a trade-off between size and power in the choice of kappa. But the first and higher order properties of this test do not depend on kappa. So when you just compute the limit expressions of the GMS test, kappa doesn't appear anywhere. And even in, as I said, not only first order, it's higher order. And this was shown in Federico Bugni's job market paper, right? So then this is a problem because you know that you have a tuning parameter like a bandwidth, right? Where you just say you have bias, variance, trade-off, and so on. But in your asymptotics, nothing depends on kappa. So the asymptotics don't capture this trade-off. And so when you put everything together, you cannot use that to get data-dependent rules for choosing kappa. And the choice of kappa is, quote-unquote, in the air, okay? And the literature never figured out how to come up with a data-dependent way of choosing kappa. So there are rule of thumbs that people use. You'll see kappa n being square root, say log n, which is something that comes from the law of iterated logarithms, as you recall. And people will use that. But of course, 2 times that, 3 times that, 4 times that is going to work as well. Some people just use square root log n. But it's a tuning parameter that cannot be picked in a data-dependent manner. So that's that. Now, when it comes to power, there's something cool about this, which remember, all these tests are going to use the same test statistic. So talking about power is just only talking about critical values. And what's the test that has the best power? The test that has the smallest critical value. So talking about power here is just comparing critical values. If you can tell me that one critical value is smaller than the other one, then you tell me that one method is more power than the other one, okay? That's one layer. The other layer is that the size of the critical values here, at the end of the day, depend on how many moments you take as binding, how many moments you take as slack. The more moments you consider as binding, think about the least favorable critical value where everything is binding. You just use 0 as your function s. Well, that's the least powerful one. And the better the method, at detecting inequalities that are non-binding, the more powerful your test is going to be. So I wrote here at the top that typically GMS is more powerful than subsampling. What does it mean? It has to be that typically GMS is better at detecting that one moment is binding relative to what subsampling does. Okay? So I'm going to illustrate that in the next example. Do you have any questions before I show you the example? Hopefully the example will help clarify. So consider this setting, okay? It's just very simple. There are two inequalities, okay? Mu1 and mu2. This is just a high level example, okay? I'm not writing the conditions and so on. I could, but it's just adding steps for nothing. Because at the end of the day, what I care about is, whether these moments are binding or not. And look what I did. The first moment, okay, is a sequence. I'm considering sequences of distributions because, again, when we think about uniformity, as I said earlier, we want to consider sequences and sequences at different rates, okay? While you can consider a lot of different rates, this is the one that I care about in this example, which is the first moment is going to 0. It's going to 0 at what rate? H1 divided by square root n, okay? So it's locally 0. The larger the sample size, the closer this guy is going to be to 0, okay? And then, for all practical purposes, we will imagine that methods are going to confuse a moment like this that is negative, but very close to 0 with something that is binding. And then the second moment, notice that it has some pi 1, which is also negative, divided by square root n, but also has kappa here, inverse, okay? So this is going to 0 at a slower rate because it's not square root n, it's square root n divided by kappa. So this is going to 0 much slower than mu1. And so in a way, you would expect that this guy, okay, which you can write, notice that, let me just rewrite this as the square root n mu2 is kappa n pi 1, which drifts to negative infinity, right? So the local, according to square root n version of mu2 is lac, okay, if you rewrite it like this. So let's see what GMS does. What GMS is going to do is going to use this rule over here. So all you need to do is to look at this quantity and see if this quantity is above 1 or below 1, -1 or -1, right? And for simplicity, I'm not including the sigma hats here. So let's do it. In the first moment, we're going to have kappa n bar, the square root n bar n1 theta. This is the function that I have over here. And now the only trick that we're going to do in this analysis is just add and subtract the true mean, okay? So let me do that. I just added and subtracted the true mean because I want to understand the limiting behavior of this guy. Okay, well now, remember square root n, oops, I don't want to do that. Remember square root n bar mu1 is big OP1. And we're dividing here by 1 over kappa n. So this entire thing goes to 0, right? Because the big OP1 divided by kappa. And now this guy over here is just H1 divided by kappa n, which goes to 0. So you see that this guy is going to 0. So at some point, it's going to be above -1. And GMS is going to treat this moment as binding, meaning it's just going to use 0 as the upper bound. Again, this is an asymptotic bound, so you need to take n to infinity. But you see how GMS is going to use this rule, Okay, and for that, it will check whether this is small enough. Well, we can see here that this is small enough. Let's do the same for the second one. We have kappa n inverse square root n bar n2 theta n if you want. And then here is going to be, again, 1 over kappa square root n bar n2 theta n minus mu 2 theta n pn. This same argument as before goes to 0. And then we have the remaining term, kappa inverse times square root n mu 2 theta n p. This is equal to, sorry, whoops, pi 1, which is less than -1. So SGMS hat 2 is going to be negative infinity. It's going to treat this second moment as slack, because eventually this guy is going to be below -1. Of course, you can say, well, you just chose these sequences such that this happened. Of course, but you can show that this holds broadly. What I'm going to illustrate here is holds broadly. For if you consider any other sequences, you're going to have this result or the result that GMS and subsampling are the same. But GMS then takes the first moment as binding, the second one as slack. Do you agree with that? Are we good there? So I said the critical value for subsampling has to be larger, because the method with the smallest critical value is the one that is going to have more power. In order for subsampling to be larger, only one thing can happen, which is this moment that here we're treating as slack. Subsampling doesn't notice this, and it believes that this is sufficiently close to 0 to treat both as binding. So let's see if that's the case. Here's subsampling, and I want to include this condition that I'm going to explain later, okay? But let's take the first moment. What is the first moment? The bound of subsampling is the square root b times mu1 theta n pn. And this is square root b times h1 divided by square root n. And this is square root b divided by n times h1. This goes to 0. That's the bound that subsampling uses, the square root b mu, right? First moment has square root b mu going to 0. Second moment, we have square root b mu 2. And this is square root b. And remember, mu 2 was pi 1 divided by kappa n inverse square root n. Let me rewrite this as square root b divided by n times kappa n pi 1. And then this goes to 0 by our club condition. No, this is, club. So subsampling believes that both of these moments are binding. And then you may say, where is this coming from? Why do you have this rate between subsampling and kappa? And I want to say, well, this is an assumption that is actually imposed in the paper by Andrews and Soares to show that their method has more power. But arguably, kappa is a sequence that is typically associated with the law of its real logarithms. So they have the magnitude of log n, square root log n, or log n, whereas subsampling, has a rate that is has to be polynomial in n. And actually, Federico Bugni showed that the best rate for subsampling is n to the 1/3. Right, that's the optimal rate if you want to think about size control. Okay, so if you now think this rate for subsampling and this type of rates for selection mechanisms, then this condition at the top holds. And it follows that GMS is better at detecting whether things are binding or not, okay? Because, quote unquote, when you have this type of sequences that go to zero, but go to zero not so fast, GMS realizes that they're far from zero and then we'll treat them as slack. Whereas subsampling is just going to say, oh, they're going to zero. I want to treat them as binding. And you can show, which I'm not going to do, okay, that you cannot build a counterexample in the other way. Under this condition, there's not a situation in which subsampling will find, say, binding and slack, and GMS will go binding. So either the two are the same, or GMS gives you a critical value that is smaller. And this is what moment selection is about in the literature of moment inequalities. How much did we understand about this? All right, but there's still something that is unpleasant here, which is we don't know how to choose Kappa, right? I wrote first and second order asymptotic properties of GMS test do not depend on Kappa. And in finite samples, the smaller choices of Kappa typically get better power, right? So I say it's not as sensitive to Kappa, but if you keep decreasing Kappa, you start gonna reject it more, okay? So what's the main idea that was proposed later on in the paper was in order to develop data-dependent rules for choosing Kappa, you need to change the asymptotic framework so that Kappa does not change with n. So remember, this is interesting because things that we said at the beginning of the class was like, well, sometimes to get better approximation, you need to let things change with n so that we capture what we want. And here is exactly the opposite. We know that in finite samples, things depend on Kappa, but Kappa doesn't appear in the limited distribution because Kappa is going to infinity, okay? And so it's like n. N doesn't appear at the end of the limiting statements, right? So Kappa doesn't appear at the end of the limiting statements. But we know that the finite sample distribution depends on Kappa. So how can we accomplish this in the asymptotics? Well, let's just make Kappa fixed, okay? So that Kappa now is going to appear in the asymptotic distribution. So the idea of the so-called refined moment selection is that it's the same, exactly the same as before, but Kappa is fixed. Doesn't change with n. Of course, there's a problem with that because the minute that Kappa is fixed, then this function s is no longer a valid asymptotic bound for square root n mu. So our initial goal of like, oh, we want s to be greater than or equal than square root n mu is broken, okay? And so the critical value that we get out of this approach is just too small. So what these people said is like, okay, if it's small, we can make it bigger. And so they introduce the idea of size correction that they call eta. Okay, so now we're going to have this selection function, and this is the critical value with this selection function. It's too small, so we need to add something else. We're going to add this eta. And if we choose eta correctly, we're going to have a valid test. So we sort of like move the goalpost in a way. We went from having one tuning parameter now to have two tuning parameters, okay? But by doing so, we can show that the first order properties will depend on Kappa, and this may give us a way of choosing Kappa in a data dependent way. Like if you just tell me your data, let's find a good choice of Kappa. Well, this problem conceptually, just think about conceptually, looks very clean, okay? You just say, I'm gonna let Kappa fix. Kappa fix doesn't work, so I need size correction. So let me just think about how to choose Kappa now, and then we'll think about how to choose the size correction. Well, the test is just this. Just use the quantile of this function over here, which is the same as this part is the same as the GMS critical value with a fixed Kappa, and then you add a size correction factor. And this is the key piece, okay? The problem is, and let me skip some of the details here because it's just going to confuse you only, okay? I have them here, but I don't want to discuss them. I want to say choosing this lambda here is really difficult. Really difficult. And it involves solving this type of optimization problem where you have to choose for all s's of these distributions here and then do it over and over and just is infeasible. So what they did, and this was the paper by Anderson Barwick, they just simplified the problem in two ways. Okay, they said let's ignore the correlation matrix of the moments. That's too difficult. If you look at these expressions, they depend on the correlation matrix. Okay, so you sort of like have to compute for all possible correlation structures of the moment inequalities. Let's simplify that. Let's just look at the off-diagonal element, the smallest off-diagonal element that they call delta. So we went from a problem where we have a correlation matrix k by k to a scalar, where we just say we just look at the smallest off-diagonal element. And then this problem over here, which I said I want you to pay attention, I just want you to look at that we have a supremum here over all s's from negative infinity to 0 in Rk. Well, that looks like a complicated problem. We're going to replace that with negative infinity and 0. So s can only take two values, 0 and negative infinity. So they make these two simplifications. They provide some numerical evidence in favor of these simplifications. And at the end of the day, they present a table that has values for k, which here is p, up to 10 only. And this is the paper did all this work to provide a table for 10 moment inequalities. If you want to implement this method with more than 10 moment inequalities, you don't have a table. And you have to redo all this by yourself, which nobody will do. So the method is conceptually clever. Computationally is a nightmare. Okay. And so how do you use this table? Let's say that you're in a case in which you have less than 10 moment inequalities. Well, first you need to compute delta. Remember, delta is the minimum value of the correlation among the moments that you have. And then you just look at that correlation, give me a number, 0.78. So you go to this table and look for where 0.78 falls. It falls here. Well, it's let's take the negative 0.78. All right, here. And so that tells you that kappa is 2.6. And eta is the sum of eta 1, which is here 10.04. And then the other part of the eta depends on how many moments. Let's assume that you have 9. So you have 0.45. So your eta is going to be 0.104 plus 0.45, which is roughly going to be 0.554. And that's the size correction factor. And so you go back, you use this kappa, use this eta, and then you implement the test. But in reality, and even though this paper was published in Econometrics, okay, and it was later studied by Adam McCloskey, who derived more results about this, it's just, as I wrote here, computationally infeasible for having more than 10 moments. And so you say, like, well, is 10 moments like too big? Well, here I have two papers that are applied on this, and then you have one that has about 500 moments, okay, and then you have the usual Sealy-Berton tamer, which is 2 to the number of firms plus 1, that typically goes above 10 very easily. How many moments do we have in that application that we're doing, Amilcar?
64.
64. So you see that it doesn't work. Like, it's just only in a very stylized situation you can have this, and that's why I decided to skip some of these details. That's why I don't want to get into the details. I just want you to be aware that the refined moment selection exists, and I don't want to be unfair to the paper because expose is easy to criticize. The problem of trying to choose kappa is difficult. Okay, and this paper followed an approach that was conceptually clever. The problem is that it had to deal with the computational nightmare that this approach eventually introduced, and they managed to do it, for some simplified cases in less than 10 moments. But as I said, this table took a lot of work in this paper. Nobody is just gonna do this if you have more moments, because this problem over here is just computing the size correction is just too difficult. And remember that we're in a context And we have to do this test for every value of theta. So it's not that you do it once and you call it success. We just have to do this over and over and over and over. Is it's certainly computationally infeasible to do a confidence set for a parameter theta by using this approach. But the idea hopefully makes sense. All right. This leads to the last method. Eventually people really didn't like this Kappa business going to infinity and this asymptotics that didn't depend on Kappa. So, I have questions here. Do you have questions? That was the idea about refined moment selection, right? Let's do the asymptotics that are more honest with Kappa, but the main conclusion is that it's really difficult. And then it came this paper by Romano, Shake, and Wolf that provided a completely different approach and essentially solved the problem. Okay, but they just thought about it in a different way. They said we're going to do a method in 2 steps. In the first step, we're going to construct a confidence region for mu. Okay, for some small, I wrote here, significance level that I'm going to call beta here. It's just we're going to do a confidence region for mu. And in the second step, we're going to use this confidence region to have some information as to whether these moments are negative or not. The problem with this approach, when you think about it, is that confidence regions make mistakes. Okay, so they're like, with some probability you get what you want, with some probability you don't get what you want. And so in order for the 2-step approach to work, you will have to take into account the probability of making mistakes. Okay, it's not just simply behaving as if the confidence set contains what you want. So here are the 2 steps. In the first step, you're going to construct a confidence region for mu that we're going to call M. Okay, it's going to be a 1 minus beta confidence region for the square root mu. And so we want this to satisfy the following. The lim inf of the inf of the inf of the probability that a square root mu belongs to our confidence region is at least equal to 1 minus beta, where beta is going to be some small significance level, which in particular is going to be smaller than alpha, which is the coverage that we're going to want of our method at the end of the day. Okay, so if you're doing 5%, beta is typically going to be like 1%, say, or something like that. Okay. So, and in particular, we're not going to take any confidence region. We're going to focus for computational reasons, okay, into upper right rectangular confidence regions for mu. So what are these? Like, imagine that, let me go back to the blue. Imagine that we have only 2 mu's, mu1 and mu2. An upper whatever rectangular confidence region is going to be something that looks like this. Oops, I'm going over. Okay, that's the upper right rectangular confidence region. Takes everything to one side. And so when you write it down, it just looks like this. Okay, it's just all the mu j's less than or equal than the sample average plus standard deviation square root n and the quantile that you get, from this problem over here. And this quantile and in this paper is just going to be computed by the bootstrap. Okay, you can show that the bootstrap gives you a nice and uniformly valid upper right rectangular confidence region for square root n mu. Okay, so this is the first step. Just do a rectangle. Okay, in the second step, we're going to use that rectangle to decide whether a moment is binding or not. And so what's going to happen is that we're going to intersect that confidence region with the areas that we care about. And in this particular case, what's really nice about this paper is that the selection function S is going to have a closed form. And it's just going to be the minimum between the boundary of your confidence region and 0. The minimum between that and 0. And so when you go to this picture, where's the minimum between that and 0? You have to do that coordinate by coordinate. Okay, when you look at mu1, the minimum between our region and 0 is that point. Okay, so S hat 1 is going to be negative. And when you look at mu 2, the minimum between that and our point is just going to be 0. Okay, so here in this region, S hat 2, this green is just really bad. S hat 2 is going to be 0, and S hat 1 is going to be negative. Why is this? Look at the confidence region. This confidence rectangle, does it include 0 for the component mu 2? Yes, 0 is included there, right? Does it include 0 for the component mu 1? No. It just only includes negative numbers. So when you look at the confidence region does include 0 for mu 2. So you say, well, it could be binding, okay? And does not include 0 for mu 1. So you say it's luck. And that's what the method is doing, is looking at the confidence region and trying to ask ourselves, do we include 0 here or not? And that's what you're doing. And then in the end of the day, it has this closed form over here. So what is a two-step critical value? Is an estimate of the auxiliary distribution using this selection function, but at level 1 minus alpha plus beta. You don't do 1 minus alpha, you have to do 1 minus alpha plus beta. And this has a close expression for the function S, which is a key feature that makes this method really computationally tractable. Okay? So, definition, the two-step method is a test that rejects whenever the test statistic is greater than the critical value that uses this selection function and uses level 1 minus alpha plus beta. And why does this work? Well, because if you compute the probability that your test statistic is greater than this critical value, this is less than or equal than the probability that, you reject when you use the true centering, a square root mu, right? Instead of this S, plus the probability that your confidence region does not include true mu. This is the probability that you make a mistake. Okay, so if your confidence set includes the true mu, then S is going to be exactly equal to mu. Okay, it's going to be a valid upper bound. But there's a probability that you're going to make a mistake. With what probability do you make a mistake? Well, with probability beta, because you constructed a confidence region with that property. And with what probability are you going to cover the first term? Well, with probability alpha minus beta, because you did a test with level 1 minus alpha plus beta. So this is, less than or equal than alpha minus beta plus beta is equal to alpha. And the method works. And there's no kappa in this method, right? The only additional tuning parameter is beta. But beta is not a drifting tuning parameter. It's the coverage of your confidence region. It's a number that doesn't drift to 0 or infinity as n goes to infinity. And so, in that sense, you can just describe how things depend on beta. And so, note here, the argument hinges on simple Bonferroni type inequalities, which is what we did over here in this slide. And then it incorporates information about a square root mu, which is essentially in the confidence region. And by doing this, they managed to get an asymptotic framework whose properties depend on beta. So now your tuning parameter that is beta, you can say something about. This method remains feasible even for large values of k, so it doesn't have to use all these tricks for the refined moment selection. And despite the bound being crude, because as I said, it's a Bonferroni type inequality, it's, at least in simulations and different papers, it remains competitive in power. The main selling point of this paper is that it's the first paper that shows you can have this type of asymptotics, okay, in a computationally feasible manner. And this is what separates this approach from the previous one, where it's essentially computationally impossible. Questions? All right. So as I said when we started, I'm not going to talk about subvector inference because I don't have the time. But I'm just going to tell you what the problem is. I want you to go back to the idea here that theta is a vector. Okay, so imagine that theta is theta 1 dot dot dot, and suppose it has dimension q. I don't know, right? And so everything we said was about a test that was going to take the form t and theta less than unequal than a critical value that was 1 minus alpha, and it depends on theta as well. And if we want a confidence set or confidence region for theta, we need to explore the parameter space for theta, capital theta. Now, think about how an usual applied paper goes and what do they present, right? Just go back, forget about moment inequality. Just think about in general. Well, people will present a table that will look like this, right? It was like theta 1, theta 2, theta 3, blah, 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 theta q. And then here's going to be an estimate, a standard error, some, say, p-value, some confidence interval, perhaps, and so on, right? That's how a usual table looks like, okay? And so when you look at a table like this, you notice that we are very used to look at results component by component as opposed to like an entire vector, okay? And, this is an easy way also to report results when Q is large. Suppose that Q is 20. I mean, this is not huge, but it's just something, right? All right. So then, of course, you can do everything we discussed so far. You get a confidence set. In step 1, you get a confidence set for theta. And in step 2, you project your confidence set to each coordinate. You can do that, but that will be conservative. And it could be really conservative. The larger Q is, the more conservative it will be. So the question is whether you can just, if you want to focus on, say, theta 1, okay, only, can you do a confidence set for theta 1 only, okay, without paying attention to theta 2 through theta q? And then you will know from everything you know, it's like, well, we can profile, right? We can just have a test statistic that only depends on theta 1 if we just compute an infimum over all the thetas that are not 1, okay, in some space. Right? So that's what we do in other contexts. You profile. You just minimize the other ones. This, in the context of moment inequalities, is really problematic. Because now, all the thetas and whatever are going to be random. And then there are going to be sequences of random things. The math gets complicated. The ideas that we describe in moment selection are such that moment selection no longer gives a valid upper bound. Actually, 0 is no longer a valid upper bound for these things, and everything falls apart. And can it be done? Yes. What's out there? Essentially, there are 2 papers. One is a paper that I wrote with Federico Bugni and Xiao Shashi, and the other one is a paper by Kaido Molinari Stoy. Now there's a new paper by C. Andrews and Ariel Pekes that recently came out, and they're working on that. People are working on this. And when we started working on this, we thought that we were going to provide a computationally tractable and appealing approach, because I said my intuition was if you have a 20-dimensional object like this and you just focus on one, you're going to do a lot better in terms of speed and so on. But there's a trade-off, because now the method becomes more complicated. If you only care about one dimension, then you definitely gain, and we show that in the paper. But if you just want to present this table and you want to do one by one, computationally is not going to be a lot better. Maybe not as conservative as projection. We actually show that. So you can do better in that sense, but not from a computational point of view. So I'm going to skip all this, okay? And it's in the paper, and we talked about it. It's an area of active research these days. So I doubt that anything that I can tell you today in terms of you should do A, B, or C is going to stick to moving forward. Whereas the literature on choosing moments and so on is basically this. And if you understand these methods, somebody comes with something new tomorrow, it's just going to be very similar to that in some way. And by the way, I should say these methods are not all the methods that are out there. Of course, it's a survey and there are other methods. And, it's always tricky because people feel left out when you don't cite whatever they were doing. And so the intention is not to do a comprehensive thing. It's just to say, more or less, everything feels like one of these 5 methods. Okay. But there are other things around. All right. So let me skip all these slides and go to whatever here. Extensions. I'm going to mention some extensions and we're going to be done. The first extension is the one on many moment inequalities. Okay. And this was paper by Chanosukov, Cheverikov, and Kato. So where they said in many applications, the number of moment inequalities is really large. Remember that I showed you one where there were 500. And then if you think about entry games, it's 2 to the m, whatever. So like the question is, what if we start thinking about K, the number of moments? Okay, now let's call it Kn going to infinity. The problem with this is that now we require different asymptotics, right? Because we are having a lot of moments, so we cannot use the usual CLTs and so on. And so I wrote here requires asymptotic approximations for normalized sums with increasing dimension. So you need the right tools. And the right tools were actually developed in a really good paper also by Viktor Shinosukov, Cheverikov, and Kato, which is an annals paper about CLTs for high dimensions. And what they show is that in this setting, you can consider models that have this feature. So really, Kappa is a lot larger than n because it grows exponentially with n. So you can consider a lot of inequalities, okay? So at that point, you just don't care how many inequalities are. But it's important that you use the right test statistic. Before I said, you can use any test statistic, and I just said T. Well, now, no, you need to use this T max, and there are reasons for that. And the idea is that if you just ignore the maximum here, right? So you have that square root n bar divided by sigma for one moment. Well, that's going to be normal, okay? And you don't want to sum an increasing number of normals because that, depending on how fast it grows, and we're saying here it grows really fast, it's going to explode. But what you would want to do is just to look at the maximum of those. And so when you look at the maximum, okay, then you are less sensitive to how fast the number of elements that you're taking the maximum to growth, because you're just taking the maximum of a normal. And we understand the properties of that. And what they show in this paper is that the following critical value that is fixed as a closed form looks like this and leads to a uniformly valid test. So what is this? It's just the CDF, the inverse of the CDF of normal at 1 minus alpha minus 2 beta, okay, divided by kappa. And then you're going to see later why beta shows up and so on. What's beta? As you can imagine from the previous paper, you can have a guess of what this is going to be. But the point is that if you ignore that the critical value has a closed form, it's very easy to compute, doesn't require simulation, it's just something you get from a computer. And it depends on theta, which sometimes I get these questions like the critical value depends on theta, in this case, implicitly in the choice of K over here. This is the equivalent of a least favorable critical value. Okay, and you see that in this K over here, where essentially you're saying that all of the moments are possibly binding. Okay, hidden here you have that. But as opposed to the least favorable critical value that we showed before, there's evidence that this critical value is a lot less conservative than the least favorable critical value. The approximation is different. So it's a different type of approximation. And so it could be that it's a tighter approximation. So I think that this is a very good starting point for a critical value. Okay. Closed form doesn't require simulations. It's fixed. Okay. For every theta, and allows you to, if you have to do test inversion, to have a sense of where things are very quickly. Okay. Now, that doesn't mean that you cannot do moment selection. As I wrote here, it's possible to improve upon this critical value by incorporating some information about whether moments are binding or not. And so what this paper proposes is to do 2 steps. Okay. In the first step, use a preliminary selection step. Okay, so step 1, what you do is you estimate kappa hat, I'm going to call it here, okay, which is how many of the moments are binding. And what are the binding moments? Are those where, again, know what you're doing here. You're looking at square root n bar sigma greater than some critical value. Is this same as the GMS? Okay, 0, except that notice that 2C hat CCK and K is not a drifting sequence, it's a quantile. Okay? Notice that this guy is the same as this one, right? So it's that critical value. So closed form is known. It's just twice that critical value for 1 minus beta level. Okay? And then in the second step, you just do this, which I think I have to check. I forgot this. You should look at the paper, but I think that here, this critical value shouldn't be 1 minus alpha. It should be 1 minus alpha plus 2 beta. I check that when you look at the paper. If you're going to use this, I may have made a mistake. I need to check this. I'm going to do a cross here so that I remember. But anyway, the 2 steps are, in the first step, you compute this critical value. Given that critical value, determine which moments are binding or not by looking at how many are like close enough to 0 and this critical value. And then in the second step, you just use the same critical value where instead of having K, you have K hat. You see the difference there, right? It's like tiny, but that's the trick. You're not using K, you're using K hat, okay? And so this is how many moment inequalities work. This approach, again, if you read the paper, it's sort of like hard to understand, I think, how clean this paper is and how the improvement that they're doing over the literature if you do not understand, for example, the 2-step approach in Romano, Shake, and Wolf, okay? But this paper is highly influenced by, for example, Romano, Shake, and Wolf when they decide to come out with this like 2 steps, okay? So you see how the idea, again, is to use a 2-step and no drifting sequences. There are no drifting sequences of tuning parameters, okay? Here, the only tuning parameter, again, is beta, which is the same in this 2-step. It's the only number. And then, as I wrote here, they need beta, in this case, to be positive, but smaller than alpha divided by 3. So, alpha divided by 5, alpha divided by 10, which I said before, rules that still work here. It's a tuning parameter, but it's a non-drifting tuning parameter. And this is a method that I think he has the advantage of providing a first picture in the most computationally efficient manner. So if somebody's starting to do an application of moment inequalities today, I'll say this probably is the first thing that I would suggest you do, okay? Because it's as fast as you can get to get a sense of where things are. And it has good properties. And it has the advantage of being a method that doesn't depend on the number of moment inequalities. And remember, go back to the reveal preference setting, right? Where we discussed at the beginning where I was talking about the ATMs. And then we said like, oh, in Peck Sport Juan Ishii, they consider +1 and -1 because immediately you have many moment inequalities. And of course, at the time they were concerned about having too many moment inequalities because all these methods, that were being developed were for fixed K, right? So you really needed a fixed number of moment inequalities. Whereas when this paper comes in, says, you know what, consider as many deviations as you want. Even if that will lead to a lot more moments than the exponential of your sample size, right? So you can have an application with 2,000 observations and perhaps, 20,000 moments. That's fine. We can handle that. And before this paper, that wasn't an option, okay? So it just gives more freedom in terms of the things that you can consider. Now, this is the first extension. The second is not an extension. It's a slightly different problem, which is conditional moment inequalities. Here in this slide, I'm just going to give you references. There are 2 main papers in this that were the paper by Anderson Shi and Shinosuke, Lee, and Rosen. Okay, Anderson, she said, look at the identified set here. It's the same as before, but we have a conditional moment inequality, which we know that in economics we often get conditional moment inequalities. Well, Anderson, she just showed that you can replace the conditional moment with a lot of unconditional ones for right basis functions that they call G here. Once you do that, it really looks like GMS, but more complicated. Okay. But if you're dealing with conditional moment inequalities, Anderson Shi is a key reference. And the other approach is Shinosuke, Lee, and Rosen. And what they do is just they specialize in the so-called intersection bounds. When you have an upper and a lower bound that are intersecting things. And so they consider null hypothesis of this is the mu tilde, which is the conditional expectation. They write it as the supremum over the conditioning set here that they call B less than or equal to 0, and they develop a test for that. The test is sufficiently different to everything that I said that it doesn't make sense to discuss it, right? That will require a separate lecture. And you could discuss Anderson Shi, but it will require a lot of extra notation. I believe that if you understand, once you review the material or read the paper that I wrote with the SEAM, and you understand what's going on there, you can certainly read Anderson Shi and understand, pretty much everything. Shinosuke, Lee, and Rosen is well written, but it uses other tools. So the connection between what we did before is going to be less clear. But my point is that if you say, okay, everything we discussed was about unconditional moments, what about conditional moments? Well, this has been worked out. And these are not the only two papers. There are some other papers out there, but these are the main two groups of papers. Okay. And they were essentially published at around this. Well, I see that 2013 at the same time, right? So these are the references you should be aware of. The last two things are getting farther and farther away from what I said, but it's, good to mention them. One is random set theory. There's an entire approach about inference in moment inequalities that relies on this random set theory. What is it? I wrote, is a mathematical framework to study random objects whose realizations are set. Instead of random variables, you have random sets. It's useful for identification and inference with objects of interest. Is the identified set. Okay, so here we deviate. Remember at the beginning where I talk about points in the set or the set itself, where the random set theory is particularly good when this set is the object of interest. It is an area of mathematics, and the first application in econometrics was in this paper by Berestianu and Molinari. Both are former Northwestern students. Okay. And they came out with this paper where they essentially show that an identified set, okay, could be is a convex set, okay, that can be expressed as the Aumann expectation, which is one of these operators in this random set theory. And then you can test hypotheses about whether the set is equal to some other set. It's very neat. The theory so far has been proven from my point of view, more useful to provide characterizations of the identified set that are very elegant, okay, than to coming up with computationally tractable methods. But, there's been progress made in these directions. And then as I said, Molinari is somebody who worked on this, okay, Francesca. And then you also have Adam Rosen, wrote papers with Andrew Cheshire on how to use this random set theory for IB problems and the like. So there's a bunch of people that have worked on this. As a student, it's tricky because you really have to invest into learning random set theory, right? And so it's not something that you're going to learn in other areas, okay? And if you talk to the supporters, which would be, so talk to Francesca Molinari or Adam Rosen or Andrew Cheshire, they're going to be tell you that you can analyze problems that, you couldn't analyze with other methods. And so this provides advantages. If you talk to the haters, they will say, this is a beautiful mathematical theory, but computationally, this is a nightmare, okay? Because you're working with sets and with sets and with sets, and um, it's arguably elegant. And whether it's going to have an impact in applied work is yet to be seen. Okay, so we'll see. But it's something you should know that it exists. And the final piece is Bayesians. Bayesians are always there, right? You want to ignore them, but I'm joking. So these Bayesian approach, okay, and Bayesians have a role to play here, because whenever you come and say that something is computationally difficult, Bayesians come with this idea that they have learned, spend their lives trying to solve computationally difficult problems. So the insight that matters is the following. This one I want to go over so you understand. In identifying models, if you just go to standard models, we want to do inference about the mean, frequentist confidence sets and Bayesian credible sets often coincide. Okay, if you're a frequentist and then you do X bar plus minus whatever, and if you're a Bayesian, you put a prior and then you can put a posterior and you can put a Bayesian credible set. At the end of the day, everything is about the likelihood. These two things are the same. It's just about interpretation, but they just give you the same answer. But this equivalence breaks down in the context of partially identifying models, and then this makes partially identifying models different. And the issue is that priors on theta influence the posterior concerning theta a lot, because there are parts of your prior that are not going to be updated by the data, because the data has now information in the set, in the identified set. It's like everything is the same. And what happens is that credible sets tend to be smaller than frequentist confidence sets. So from the Bayesian perspective, frequentist confidence sets are too wide, but whereas for the frequentist perspective, these Bayesian credible sets are too narrow. Okay, and there's no agreement in what we're doing. So, I wrote here, the lack of asymptotic harmony between Bayesian and frequentist inference is less severe when the object of interest is the identified set, as opposed to points in the identified set. So, most of the research later on in this literature has been dealing with the set as opposed to the point. And there are some papers, I wrote here recent, years go by, I should remove the word recent, but recent papers propose robust Bayesian methods and show that credible sets are also valid frequentist confidence sets for theta. It's like there are papers that are trying to claim, look, we know that there's no equivalence between frequentists and Bayesians, but this actually, can be recovered if we just care about inference for theta. But the problem is that these papers, when they talk about equivalence, they're talking about point-wise asymptotic equivalence, which is a concern, okay? Because in this literature, even though I haven't emphasized through the discussion, I did say that all the methods that I discussed so far, all of them, have uniformly valid statements in their papers, okay? So, and that's an important consideration in this literature. So when, you read a paper and so like, oh, look, frequentist and Bayesian, agree here, I will argue, well, that's not the frequencies that I will care about. I just care about another type of confidence statement that is not that one, okay? Is that what you're looking at is a point-wise statement. And if we don't care about point-wise statements, if we restrict ourselves to frequentist methods, it's unclear why you will care about a Bayesian approach if it's only point-wise, okay? So, however, there are some beliefs, okay, and there people are working just in using Bayesian methods for computational things. So, for example, Eli Tamer wrote a paper where they just use MCMC, okay, to explore the parameter space. But the inference is done in a Bayesian way. It's just that you use this MCMC things just to be able to get the confidence set. So perhaps there's room for mixing Bayesian computational tricks with the frequentist constructions and moment selection and the like to get something that, gets you the best of the two worlds, which is you have something with good uniform coverage properties and computationally tractable at the same time. From my point of view, the main challenge in this literature is that the computational barriers are still very big. And when you start working with a real application, it's quite often the case that you just make decisions to make the problem tractable, not to make the problem as interesting as you would like. Okay? So here's a reference of some of the papers that I mentioned. Okay, if you want to look, but there are others certainly. And that's about it. That's the end of this third part of the class. Questions, suggestions.